Thank you. So security, right? Where Brendan brought up this point, using BPF for security. How is it different? So I'm here to talk about why security is such a difficult topic. Most of the time when people talk about eBPF, they talk about observability and monitoring. And most of the tools, they start with observability and then they try to extend towards security. Well, this is a perfect recipe for disaster. When you try to use such kind of tools for observability and then they try to migrate towards security use cases. And I'm going to give you some examples. Yeah, thank you. So, typically the enforcement part, if you want to block something, typically the strategy that is adopted is that you get a number of events. You have an observability engine already in place and it gives you a bunch of events. Now you have all those fancy dashboards. Now you want to take some action based on those fancy dashboards. What is the next thing that you'll do? The next thing that you'll do is based on some of the actions or combination of actions, you'll try to take an action which could be, doing some sort of remedial action. And then calling it security is the biggest problem. That's what I'm here to talk about. Taking some remedial action as an afterthought is a problem, primarily because by the time you take a remedial action, the damage would have been already done. If it's a ransomware attacker, your sensitive assets are already encrypted. If it's a crypto mining attack, the biggest problem is if you allow an attacker to execute that code on the target environment, attackers are the most savvy people who know which knobs have to be turned off. So if you allow that, you're already in a uncomfortable spot. So brief background as to, why we started AccuKnox. But again, I'm going to talk about an open source project that we have been working upon called QUIC. And some of the reasons why we started it in the first place. The primary reason why we started in the first place is because there was no engine out there which could do inline mitigation, which means that stopping an attack before it can, even before the execution begins. Rather than if a process is found, you see that it's a malicious process and then take an action in the form of killing the process. That's the whole loop is something that we wanted to avoid, because by the time you kill the process, the damage is already done. So we looked at certain controls, like when it comes to security, it's not like you have to work everything out yourself. There are a lot of attack frameworks out there, which tells you what are the things that the attackers are going to do. It's called MITRE TTPs, tactics, techniques, and procedures. And they clearly represent as to what are the detection techniques, what are the mitigation techniques. Detection techniques are fine, if a particular file system path is going to be changed, particular process is going to be executed and all those. The detection techniques are fine. But when it comes to mitigation techniques, the mitigation techniques usually are implemented in an insecure way. And that's what led us to think why there is no such engine which can do inline mitigation wherein you can stop the attack in the first place. That's the security principle that we focused on and we built towards. Now, again, this is the point that Brendan also talked about, time to check versus time to use. This is the biggest issue when it comes to security. By the time you take a remedial action, the premise that you had is no longer true. So you do not want to use security primitives or primitives which might suffer from this kind of problems. The second is the semantic poisoning. Typically what happens is that you can put in a detection rule saying a specific binary gets executed. You would like the user to be alerted about it. Most of the time what happens is a hard link is created or a symlink is created and the target executable is executed through that symlink. That typically is called semantic poisoning. You do not want to use security primitives which have problems wherein they cannot identify these symlinks or hard links. For example, if you simply have a kprobe at execve, which is a system call, and you say that I'm going to monitor all the system calls, and if I see a particular binary, let's say for example, cryptojacking binary xmrig, I'm talking about real problems here. These are the problems that we solve on a daily basis. If you want to identify whether xmrig is getting executed, you attach a kprobe, you check what is the system call argument, and then you decide based on that. But if the attacker uses a symbolic link, that's a very simple technique, uses a symbolic link then to point towards xmrig, you won't get the executable path name in the first place. So semantic poisoning is a big problem. The reason why I'm talking about this is because there are certain solutions in the eBPF space and BPF space which can handle these problems. None of these are decade old, but some of these are upcoming primitives which have been just upstreamed in the Linux kernel like in 2019, which are gaining momentum. Not a lot of engines are making use of that, but most of the engines have now started looking towards it. Then obviously ability to allow specific action and deny all. That is something that most of the engines are now taking it seriously, as you might possibly think, because of the zero trust initiatives all across the world and in the federal spaces. Inline and preventive mitigation, again, I can't stress enough on this particular point, because if you do not have that kind of enforcement in place, you do not have a security strategy in place. Now, when it comes to kernel security primitives, I'm going to come to eBPF very soon. When we talk about eBPF, there are two aspects, right? One is the networking aspects, where you get a packet at a particular hook point. It could be TC, egress, ingress, XDP. What you can do is you can redirect that packet, or you can drop that packet. That allows you to do enforcement, right? Basically, once you drop the packet, you're stopping the connection in the first place. That allows you to do enforcement. The same is not true for the systems operations with eBPF. So if you attach a kprobe, that kprobe gives you a bunch of information, but you can't tell the kprobe to actually return failure from there. I wish that functionality would have been available, but it is not, and there is no way to enforce just using eBPF for some of the system calls. For example, if I want to say, I do not want delete command or unlink system call to be called at all in this particular container, it's not possible using kprobes, I'm saying. It's possible using certain other things, I'll come to that. Then there are Linux security modules. These are the oldest. Since kernel 2.6 onwards, we had AppArmor SLNS. Most of us already know about it, and if anyone has dealt with it, the first thing that most of the people do is turn it off, because it's so goddamn hard, right? If there is a policy violation and something stops working, the first thing that the users do is turn it off. There is in fact a website which says do not turn off slnx.com. Okay, so you can Google about it. Then there's seccomp and seccomp BPF. I think in the previous talk someone touched upon it. Quick overview. Seccomp, it allows you to sandbox a process wherein it can enable only 4 system calls: read, write, sig, return, and I forgot about the 4th one. These are the 4 system calls that it will enable, and everything else will be blocked by default. That's what seccomp does. Typically, the use case for seccomp previously was CPU renting, which means that you execute a process, that process is in execution stage, you have data plane operations, all it's going to do is read, write, and return to its primary program. So you rent out a CPU, apply a seccomp profile such that that process cannot do anything apart from these 4 actions. That was the primary use case for seccomp, not for security, even though it gets touted for security. Then comes seccomp BPF. With seccomp BPF, what is the primary change that happened was you can filter based on BPF bytecode. That's the most important change that happened. The other point is you can also take action based on the system call parameters, but the system call parameters cannot be dereferenced, which means that if you have a direct constant as a parameter, then you can use it. But if it's a dereference parameter, which means if it's a pointer to the actual value, you can't use the real value. You'll suffer talk-to problems there, and basically it won't be allowed. So seccomp BPF allows you to specify a filter saying these are the system calls which will be allowed, and that filter is essentially in the form of classic BPF bytecode. Then there are user space techniques, which has been in use since there are a lot of security tooling which use user space tooling. It's completely unsafe. Don't even go there. If you're trying to do something in the user space, something like library interpositioning, like using LD preload, for certain functional use cases you might want to do it, but not for security use cases. LD preload basically allows you to override a dynamic library calls by using your own call. Like you can even override any glibc call such as malloc and all those things using your own call in the user space. The biggest problem is most of the attackers won't use the regular libc route to call the system calls. Never. No one would use that. If I'm an attacker, I will never use that. So unless and until you're dealing with script kiddies, your solution is not going to be secure. Then there are other techniques such as binary rewriting, an interesting technique. glibc muscle updates, glibc and muscle both are libc libraries. You can update those, but again, no one in good conscience will allow any security vendor to do that, because your compliance, your FIPS certification, everything goes for a toss. Yeah, no one will allow you to do that. Now, and there are other sandboxing approaches. One is gvisor, which takes a radical approach. What it says is, we will change the container runtime and substitute our own container runtime, which is runsc. And all the system calls that get called will pass through the sentry wall of gvisor itself, which means gvisor has complete control, amazing flexibility. The biggest problem is the intrusiveness. You have to make changes into the container runtime, and maybe as Google as an organization might have that kind of impact on their customers. We certainly cannot do that, right? As a small organization. Micro virtual machines such as Firecracker and all these are gaining prominence. These are good, but the primary problem is that the resource usage for spawning individual pods is much higher, even though it's micro VMs. And then, like I said, challenges in terms of intrusiveness and needs a deployment strategy in the first place, because you have to change the container runtime interfaces. Okay, so with all this, right, we had a dilemma as to what to make use of. So basically what I'm going to tell you is our journey into why some of the eBPF primitives we ended up using, why some of the techniques we didn't use, and some of the rationale behind it. So one of the things is, well, observability and monitoring with eBPF is a no-brainer. eBPF has clearly stood out as a thing to use for observability and monitoring because of its least impact on the performance, runtime performance. But then what to do for blocking enforcement? We decided to make use of Linux security modules, LSMs. I'll go into a lot more details about these LSMs and then talk how eBPF or BPF has an impact on this LSM layer. That's my central theme of this talk. The reason why we chose LSMs is primarily because of the secure principles that it allows you to have, the talk-talk problems and the semantic poisoning issues. It doesn't suffer from those problems. But which are the LSMs? Now there are a bunch of LSMs that are available. So let me clarify before this. There are two things. One is LSM hooks, which are the hook points inside the Linux kernel. There are 400 odd hook points. SE Linux uses 380 roughly hook points. AppArmor uses a bunch of those. BPF LSM uses a bunch of those. Capabilities, you might have heard of capabilities, right? Capabilities is essentially a LSM. A lot of people don't know about it, but capabilities, if you do a man of capabilities, you'll see that it's an LSM. Lockdown is something that is used typically for locking the kernel image itself so that no one can update anything into the kernel image at runtime. SMAC, again, another mandatory access control. And again, mandatory access control is something that you'll get quoted in the context of LSMs. There is discretionary access control, which is essentially your file system paths, where you can say your owner is root, but there the root has complete privileges using discretionary access control. With Macs, even the root user cannot do certain actions. Only what you allow through the mandatory access controls will be allowed. One thing I would like to quote is that, I'm going to talk here about one of the open source KubeArmor, but KubeArmor by itself doesn't implement any security primitives by itself. That's why I've added this point here that, we stand on the shoulders of giant, which means that we actually make use of all the underlying security primitives that are already available in the Linux kernel and orchestrate it appropriately to satisfy the right security principles given the policy in place. That's our goal, primarily. I know it's a lengthy statement. Quick background about what LSMs are and why those are secure. The primary reason is because LSMs have something called as preemptive mitigation. As you can see here, LSM hooks are an explicit hook point here. So after the DAG checks are done, the SLX kernel module has to allow a specific operation, says, yes, you're okay to go ahead. It's not an afterthought. Like usually when it comes to observability-based tooling, you see some action been happening and then you take a decision. This is inline. So it could be SE Linux here, AppArmor here, anything. You can have a bunch of LSMs as a linked list here, making that decision. That's what primarily separates it. The second biggest difference is it doesn't operate at the API layer. Now, the API layer for kernel is system calls, right? Operating at a system calls is a problem because there are multiple system calls to do the same thing. For example, if you're spawning a process, you can do it with execv as well as execv 80. Some arguments differ. There are a bunch of those, and there are other ways of executing a process as well without making use of those system calls. Versus LSMs operate at an object layer, which means file objects, socket objects, inodes, and things like that. They operate at an object layer. So that's important to note, because if it's a process execution, it's a single object, you'll get a single endpoint, you'll have a single point of decision making to be done. Now, all this is great. Okay, a word about SecComp and SecComp BPF. I've already talked about it. The good news about SecComp and SecComp BPF is it's omnipresent. It means that every distribution supports it out of the box. It's great from that perspective. But it has highly restrictive use cases. SecComp has extremely restrictive. With four system calls, you can't do anything. You can't have flexible user policies that you can convert into these things. SecComp BPF opens up all sorts of possibilities, but like I said, it operates at the system call layer, API layer, does not operate at the object layer, which means that if there are multiple ways to do something, you have to take into consideration all of those layers, all of those APIs, and then have appropriate. The last point is the same point that I talked about. Rather than operating at, difficult to operate at the object references, Then, when we decided to make use of LSM, turned out we were not the only one. Think about it. It never is, right? Like, if you're doing something or you're thinking something for the first time, it usually is never the case. Why anyone else has never used LSM before? We realized it the hard way. Is because LSMs are incredibly difficult to use. And I'll give you some examples why. And SE Linux in particular, folks, is a nightmare. I can't stress enough on this. We have spent an year understanding what is the best way. Now, when I say nightmare, if you have a virtual machine which is doing a specific application execution, and you want SE Linux set of SE Linux policies, it's good enough. It's great, actually. It's not good enough. It's great. And that's why SE Linux is so popular. If it's a very predefined workload and you want to harden it, or if it's a virtual machine layer, bare metal layer, at the operating system layer, you want to harden it, SE Linux is your thing to use, best way to harden it. The primary problem that we found with SE Linux is if you have flexible policies, if you have something like a Kubernetes system, where pods are started, deleted, pods are reshuffled between the nodes, your application changes, which kind of applications are running, which means your policy enforcement rules have to adapt to these ephemeral changes, right? Like these ephemeral constructs, pods and containers and things like that. That's where the problem begins. SE Linux has something called as type enforcement, where a label is associated with every object. And if you have to change label, it has impact on all the other objects, which means that a small change in the SE Linux labels or type enforcement rules has a bigger security impact. And to manage that is extremely difficult. That was one of the problems that we faced. AppArmor is great, but AppArmor's biggest problem that we saw is that multiple versions available, each having different capabilities. The networking-based rules are not supported in the best way possible. When I say networking, what I mean is not per packet decision-making process, by the way. What I mean is which kind of accept calls are allowed from which endpoints, which kind of connects are allowed. So which client connections and which server connections are allowed at the system call level, right? That's the point. But however, AppArmor still worked for us for most security use cases, and we decided if we have to make use of the right security principles, we still have to depend upon LSMs, and let's see what is the best we can do. What we ended up doing was, we ended up using AppArmor as our primary LSM, and then SE Linux was used only for host protection in the Kubernetes environment, which means it was a partial solution. What happened? You see the support, right? Like this is the support that we had. It was untenable, frankly speaking. Like we cannot go to the users. Most of the popular, like if you don't support RHEO, you don't have any solution. If you don't support EKS, you don't have any solution out there. So we were left in a lurch, and we were dealing only with specific distributions which supports AppArmor. That was our biggest problem in 2020. Then something changed. Actually, something changed in 2019 itself, but the change was not visible out there. What happened in 2019 was BPF LSM was upstreamed into the Linux kernel by the Google folks, particularly KP Singh. I'm not sure if you know about him. Great guy. He's the one who implemented it, invented it, implemented it, and stabilized it. By 2021, almost 50% of distributions had support for BPF LSM. By 2022 and 2023, especially last year, almost every platform had support for BPF LSM. Now, I'm going to tell you why this is important. First is coverage is extremely important. Without coverage, you cannot build a product, right? Like it at least has to have 90% of coverage. If you have, and within that 90% coverage, if some of the top platforms are not included, you cannot have a solution in place. However good it might be, however sound the security principles might be, it will never get used. So BPF LSM was available in the Linux kernel. Not only did it become available, some of the distributions backported it. For example, RHEL backported it to RHEL 8, 4.18 kernel. So BPF LSM is typically available from kernel version 5.8 and above. But RHEL backported it to 4.18 kernel. I'll tell you, all this is important because, like I said, coverage is very important. If you don't have a solution which generically works across multiple distributions, then we have a problem. We maintain a Linux kernel configs for most of the popular cloud, managed cloud providers and popular distributions. We started this exercise because we are dealing in kernel level stuff, and most of the kernel configuration, we have to be aware as to which distribution support what kind of configuration. And that's why we started maintaining this. The point is, BPF LSM now, as you can see, right, the first column is for BPF LSM, second column is for AppArmor, SE Linux Landlog. SE Linux is still supported in most of the cases. There is one that is not supported here, but I think apart from that, yeah, everything else is supported. BPF LSM still has, the support is emerging. Like I said, if anyone starts a Kubernetes cluster on EKS, GKE, Azure, Oracle, IBM Kubernetes service, by default BPF LSM will be is available, but there are virtual machines out there, old instances which would still not have BPF LSM. One other advantage of BPF LSM is that it is stackable, which means that so AppArmor and SE Linux are not stackable LSMs, which means that they can't coexist. In some cases, you might see ticks for both AppArmor and SE Linux. It doesn't mean both of them are enabled. It just means that both of them are available in the kernel image that you have, but both of them cannot be enabled at the same time. You can only enable one of it. BPF LSM is a stackable LSM, so that allows you to do multi-layer security. I'm going to talk more about it in the coming slide. The primary advantage with BPF LSM is that you are not dependent upon an intermediate language that is offered by AppArmor or SE Linux. As a developer, you can decide on what basis you want to allow an operation or deny an operation. Think about it, it's very flexible. But we realize that most of the users are not going to write eBPF code by themselves, right? Like, so that's why we had this intermediate layer of QUIC which actually orchestrates those kind of things. But the fundamental point is, BPF LSM allows you to inject eBPF bytecode at LSM hooks, which have been there for the past couple of decades. LSM hooks are available across all the kernel distributions since kernel version 2.6 and above. And it allows you to do policy enforcement, which means you can actually fail. You can deny a process execution, you can deny file access, and things like that. The reason why I wanted to understand whether system calls arguments can be tampered with or changed with is because if you have that ability, you can do some sort of security layering on top of this, but I think it's very difficult. So the point is the eBPF layer, right? For every object, there exists LSM hooks, set of LSM hooks, and you can inject eBPF bytecode there to make decisions. Now, what are the other use cases of BPF LSM? One of the interesting use cases that Cloudflare and most of the other organizations use is for virtual patching. You have a vulnerability that is announced out there. What do? You can't update the application. Application update typically requires a few weeks at least, few days to few weeks time. Meanwhile, what do? You can just inject a BPF LSM bytecode into the kernel and say that particular operations are not allowed, which that vulnerability is going to target. That's about it, virtual patching. Very, very popular use case. It's been there since ever. And of course, security part, which I'm going to talk about, and the least permissive application behavior, which means that you can say only allow certain things and deny everything else. These kind of policies you can now have, basically enabling zero trust model. This is one example. I don't know whether it's visible enough. What I'm saying is that within my workload, only certain processes should be allowed network communication. These are the primitives that are allowed. Now see, it's network policy enforcement at the next level. Within a pod, you typically want only certain binaries to have that access. Like it's an atomic workload. It's trying to do one thing at a time. But typically your base image has a bunch of binaries which are more vulnerable. Or if you have an application which allows the attacker to do remote command injection, then a new binary is created and that binary is executed. That binary will have the same level of privileges as any other process within the same pod. Why should that binary have the same level of permissions as every other binary in the same pod? No. So using this, you can specify like, that this binary is allowed communication to UDP and TCP primitives. These are the file system paths, and this particular file system paths are read-only, which means, you can say that no system's binary path should be allowed to be edited. You can execute from that, but editing or updating from it won't be possible. And under the hood, all of these, for network control, these are the set of LSM hooks that have been made use of. For process and file control, these are the LSM hooks that have been made use of. BPRM's check security is particularly important. It allows you to do multiple things apart from, it allows you to check whether set UID, set GID bits are set and things like that. And then there are capability control. This is also an important thing because in the Kubernetes world, privileged containers are a big problem. And when someone enables a privilege, and there are good reasons why privileged containers might have to be enabled. For example, Calico and Cilium needs privileged execution capabilities. They're doing that work, right? Like, Cilium needs to take actions in the eBPF space, kernel space, so it needs that kind of privilege. What happens if there is a vulnerability inside that particular engine? With this, what you can say is a particular binary, a Cilium binary or a Calico binary would be allowed privilege capability to do the privilege escalation, but no other binary would be allowed that permission. So these kind of fine-tuned granular rules you can now start establishing with BPF LSM, which was not possible before. Now, what are the challenges with BPF LSM? There are multiple. I've noted down something. Obviously, the availability is only on 5.8 kernel version and above, with the exception of RHEL, where they have backported it to the older kernel version. That's a great work, it's a big time effort that they've put into that. And the other problem that we see is the kernel config might be enabled. You saw the tick there, right? Like, that means that the kernel is enabled with BPF LSM, or kernel is enabled with AppArmor and SLNS, but it might not necessarily be enabled at the boot time. So if it is not enabled at the boot time, you can't use it. So you have to, if it has to be enabled, you need a node restart to happen. By default in EKS, GKE, Azure, it's by default enabled in the kernel as well as at boot time. So, but there are certain distributions where it is not enabled at the boot time, in which case it requires a node restart. That might be a problem in certain cases, might not be a problem in some of the cases. Difficulty in handling pattern-based rules. Again, it's a generic problem with eBPF. You can't have loops that can do that kind of pattern matching. That's one of the biggest problems that we are facing. There's one more problem that I've not mentioned here, I don't know why, is about portable support across multiple platforms. AMD 64 is fine. Arch 64 is a big problem today with BPF LSM. But the fixes have been made in kernel version 6.4, which means it's still year and a half down the line. EKS has released 6.1 kernel version in the latest distribution. So it might come in another 6 months, another 1 year, 2 years at least. So anyone doing ARM security using BPF LSM will face some problems. The other thing that usually get asked is what is the performance impact when it comes to LSMs? Now, I would say as compared to any other security, if you are genuinely interested in security, there will be performance impact. If you're genuinely interested in inline mitigation, there will be performance impact. You can't skip it, right? There will be at least one check to say, is this allowed or not? And if it is not allowed, return, which means that additional check is there. There will be performance impact. The question is, what kind of performance impact does BPF LSM adds, and how does it compare in context to other LSMs which have been in use for past couple of decades? That's one big question. The biggest point is, I'm not going to go into the details of this, but there is a paper which talks about this. But the primary point that they are trying to make is, I've added a link here, there's a ACM link here. It says that the performance of BPF LSM is slightly better as compared to SE Linux, primarily because SE Linux allows you to use that common intermediate language, the CIL format, and then gets injected into the kernel space. The kernel object in the kernel space operates on that CIL format, which requires there is an additional overhead. Basically, SE Linux is trying to do things generically. There is a language, so you have to be generic enough. With BPF LSM, you are the one who's saying these are the conditions on which the return code has to be failure, which means it's very specific to what you want. Naturally will bring you better performance gains. And then, there's one more point that I've mentioned, this is the boot time parameter that is usually required. Capability and SE Linux by default are enabled in most of the systems. BPF is also enabled in most of the system, but in some systems it's not. So you have to enable it explicitly. There's one more thing that I want to go into the detail. How much time do we have, Shinu? 10 more minutes, okay. So I wanted to go into slight more detail about retpolines. It's a very nice, very quick, interesting concept. Why I'm bringing retpolines is because Linux kernel now suffers from, retpoline was introduced because of the speculative attacks brought in by Spectre. Everyone might know about it. It was a big problem, right? Intel had to make some amendments, but the Linux kernel had to be changed. Wherever indirect calls were being made, LSMs are an indirect calls, wherein you have a pointer to that particular LSM, and then that particular pointer takes an action. So here you can see, right? What happens is in the speculative execution attack is that attacker will try to, it's a side channel attack, which means that the cache will load things from the future execution into the cache, and the attacker would be able to see that. That's basically the side channel attacks, which means that if you're executing instruction 1, instruction 2, 3, 4 are already loaded into the system, and then if those instructions are not to be used, they get discarded. Otherwise, they execute sequentially. So the side channel attacks, what they do is they are able to see what the instructions 2, 3, and 4 are, or the data sets for 2, 3, and 4 are, and then leverage it to their advantage. What retpolines have done is essentially added this kind of, so you see here there is a function pointer here. In the assembly instruction, it gets converted into a thunk. You can see here, this thunk is essentially, this is the retpoline mitigation that is put in by the kernel developers. What it does is, if you see, right, this has to call setup target, which means this has to be called. But they have introduced an intermediate dead loop, so that the speculative engine basically sees this dead loop and keeps rotating in this dead loop, but the actual jump is happening here from here to here. So that's how the speculative execution attack is prevented in the Linux kernel today. I never saw such an easy explanation anywhere else, so that I thought of bringing it up here. It was relevant in the context of LSMs because LSMs is the primary, LSMs, everything, most of the things are related to indirect jumps. So it has direct impact on it. Unsafe security practices, there exists a BPF helper function, BPF override return, which allows now system call argument changing. This allows you to change the return code of a system call. Very powerful, but is never enabled in the production system for good reasons. And this is the man page, right? I don't want to talk much about it. It has security implications, and it's enabled only for test systems for error injection and test things. So you should not depend upon it. Second is the seccomp notify. Again, this is a new development. With seccomp, what happened was, in the kernel space, you can say these are the system calls that should be allowed using BPF filter. But then what seccomp notify allows you to do is, if there is a system call that you're interested in, you can send it to the user space, and the user space process can take a decision whether it has to be allowed or not. But then it supports from TalkTow, right? Like the moment you send a system call invocation to user space, and then a kernel is waiting, it will suffer from TalkTow attacks. And again, the man page is very clear that you should not use this for security purposes. The primary use case why seccomp notify was introduced was to enable rootless container runtimes, such as Podman. They make use of seccomp notify. I wish I could go into the details. It's a very interesting topic. I can't. So one of the one of the difference between some of the popular engines, all of these are CNCF projects. What happens is that, in the case of SysDig, what happens is that a kprobe is called, execv, a kprobe is sent to the user space policy engine, which says oh, it's a malicious thing. You can take an action, kill the process, and send an alert event to the user. That's fine. So that's one way of remediation. Tetragon is another CNCF project which allows you to do the same thing, but from the kernel space itself. So you can send the kill signal. You can do a BPF send signal from the kernel space itself, such that the time for execution is much less for the attacker. But it is argued that, regardless of however less the time is, the moment you allow any instruction to be executed, it's a post-attack mitigation point. Yes. First, in context of Falco. No, syscall is allowed. Syscall is allowed. And the kprobe gets executed here. Kprobes, the eBPF kprobes, eBPF bytecode execute. It sends the event to the user space using ring buffer, per buffer, whatever it is. In the user space, the policy engine sees that, okay, this is the binary name. Is this a malicious binary? Yeah. No. It's already executed. That's the important point. Very important point, by the way. So system call is not waiting. It has already executed, and it is successful already. So the target process is already executed. That's a very important point. And that's why it is called post-attack mitigation. That's why it is essentially called post-attack mitigation. With LSMs, essentially what you can do is you can say that if a particular things match, you can deny the system call in the first place. Not system call, the object level access in the first place. As well as system call, you can use seccomp BPF, LSMs to deny this execution. So that is why this is called as preemptive or inline mitigation. One of the fundamental differences when it comes to security engines. That's about it. That's all I have to say. The important thing to note is it's very easy to fall under the temptation of using insecure principles to expand the coverage. We had kept ourselves away from it. I don't know how long it will last, but as of now, we have been successful. And fortunately, we have been helped by the kernel community in some way, shape or form, because we were present at the right time, at the right place. We had a solution in place, and BPF LSM was introduced later. And we said, oh, this makes sense. Let's add support for it, and let's wait it to be adopted by the broader community. Year and a half down the line, we saw that the adoption increased, skyrocketed. And QUIC became the first engine to support BPF LSM in the first place. That's all. Thank you very much. Any questions?
Yeah, I have a query. So basically, you're achieving this hooking via the configurations in the
Yes.
YAML file, right?
Yes.
So how comprehensive is the list of
That's a great question. Yeah. So how comprehensive is this, right? Eventually, we'll end up having a standard of our own, which means it will compete with SE Linux AppArmor. We don't want to do that, right? So what we have targeted is 4 things: network primitives, process primitives, file primitives, and capabilities. 4 things, which we see as the biggest impact when it comes to privilege escalation attacks, which comes to any RC attacks or cryptojacking attacks or anything like that, ransomware attacks. Someone was talking about ransomware attacks. Yeah. So we have. It's always possible to expand. Like in the context of 5G security, this is QUIC started getting used in the context of 5G security. I talked about it in Infosys, right? Outside of our knowledge, it started getting used of, and they requested certain primitives to be added. And based on a real use case, we had that kind of support, but we try to keep it generic enough. And you can see, right, that we have tried to keep it very simple. And this is a full policy which secures Jupyter Hub Notebook. Today, Jupyter Notebook is considered to be a remote command execution toolkit. By nature it is. Programmers are allowed to execute their code into the target environment programmatically. That's the nature of Jupyter Notebook. There are a lot of concerns, and AI stacks are making use of Jupyter Notebook. There are a lot of concerns that the users, the genuine users, might take advantage of the system and push in certain things, attack binaries and things like that into the target system. How do you sandbox? This is a simple thing which can actually sandbox the whole